since we know chromate ester forming is on our mechanisms on the final, we should also know that if we know that one, we know Fischer esterification as well. Both mechanisms start exactly the same. You got to protonate your chromic acid or your carboxylic acid. Whichever ick acid you have, protonate the double bond to O. Chromic, protonate the double bond to O. Carboxylic, protonate the double bond to O. Get an oxonium in both instances. HO carbonyl CH3 with an H plus. Here, HO chromium. HO chromium, double bond O with an H and a plus. Next step's the same as well. Alcohol, lone pair, attacks the chromium in the top one because that's got the double bond to O, and the oxonium neutralizes this way with resonance. Lone pair on the O attacks the carbonyl. Why? Because that's the one with the double bond to O that got protonated. Same mechanism so far. No difference whatsoever. Now we have an oxonium on the green O. Oxonium on the green O. And it's bonded to the chromium here. New OH on the bottom. Old OH is everywhere. And we have this one here. New bond to a carbon that has an old OH here. Methyl. New OH up here. You made sulfate ion in the very first step. I'm going to squeeze it in here and down there as well. That's what you're going to use to neutralize this last oxonium. Lone pair grabs H. O gets lone pair. Lone pair grabs H. O gets lone pair. And O is attached to chromium. Both these reactions are down to the step where you need to do a dehydration to get to the final result. So I guess you could say we've made the hydrates of the final products, and you would be correct. Let's see, I'm going to deprotonate the OH on the bottom on both examples.
The hydrate basically is when the OH is still there.
Now the hydrate has water extra compared to the final product. This has to lose water to become this. This has to lose water to become that. And it's acid catalyzed dehydration you're finishing with, which looks a lot like acid catalyzed tautomerization. These are almost identical. You need both the acid that we've been using, which is sulfuric acid, and its conjugate base. Need both of those. Not fair, I know. What's the base do? What do bases always do? Grab a proton. Yes, that's the next part. She said make a pie. She's correct. Grab a proton in both. Make a pie in both. Make water leave in both. It needs to pick up a proton on its way out. That's what the sulfuric acid's for here. There's your water. Same story here. OH has to pick up a proton on its way out. And you're done.
Not bad. They're not bad.
And for the top one, I'm just going to remind you, chromate esters are not stable, unlike the carboxylic ester down here, which is very stable. I'll show you the oxidation step on the one above, since we're here, and it doesn't happen on the one below. And we'll just put a nice baby blue arrow. When this one's done, it becomes H3O plus, HCrO3, and in this case, a ketone. And the arrows look a lot like tautomerization again. Just remember, there's an H here that's not on the same carbon over here. It needs to be grabbed by water. Chromate esters do this. Carboxylic esters do not. And there's how chromium gets reduced. Chromium is now +5, which is more stable than +6. There's the oxidation step. I'll just write it down there. Got to make the ester first, and then you do the oxidation. And
8 points and from
8 points.
wow, really?
Yeah. Big picture. And there we have it.
I thought the chromic you said on the last video was 12.